In this video tutorial, we're going to go over an example of solving an integer program using branch and bound. Here I'm taking an example from the book, so I've just written out here, this is problem 11.7-10, and I've just taken it exactly from the book. We have a minimization problem with 5 variables, 3 constraints. All of the variables have to be greater than or equal to 0, but the first 3 variables, x1, 2, and x3, have to be integer. We're going to solve this using branch and bound, so using these LP relaxations in order to solve them. With that, I just want to remind you of 3 stopping criteria that we need to know about when we're branching. So if we get a solution, so we're at a certain node and it's integer, then we can stop. We'll emphasize this more with the example. If the bound that we found is worse than our best known integer solution, so a feasible solution, then we can stop off at that node. And if we get an infeasible LP relaxation, then we can stop branching at that node. So I think these are illustrated easier with the example. So I've taken this IP and I've plugged it here into Excel. So I just have my 5 variables. These are the coefficients of the objective. Here I have the coefficients for the 3 constraints. This is the current bound saying each of the variables have to be greater than or equal to 0. I then have put in my decisions. So this is where I'm going to store them. And then here I've taken the constraint and said the sum product of this row times these decisions, and I'm going to store it here where my objective, and then the same thing for each of my 3 constraints. With that, I'm going to now start. The first thing that you need to do is we're going to have a node here in our branch and bound tree. I'm going to solve the LP relaxation. So all that is my initial integer program, but I'm relaxing the part where I say that certain variables have to be integer. So I'm going to plug this into solver, and it's switched over. Let me just put that here and reset. So we're starting from scratch here. With that, first I need to plug in what's my objective, so I'm storing my objective there. I want to minimize. What are my changing cells or my decision variables? I'm going to store them here. I'm then going to add my constraints. So here I have, keeps on switching over. Hopefully this one fixed. Okay. Here I'm going to say that these have to be greater than or equal to the right-hand side. I'm going to add that. The only other constraint then is that my decision variables have to be greater or equal to, nope, we're not saying integer. That would be cheating. We're doing it by branch and bound. We're greater than or equal to my bound here. So I'm just greater than or equal to 0. I'm going to add those 2. I'm going to solve using simplex. And that's all I need to do for now. Again, it switched over, so hopefully now we will have it all. So I need to pay attention to this solver box. I need to make sure I have a feasible solution. So here it says solver found a solution. Great, this is what I want. I want a solution. And so what do I notice here? I notice my objective function value is 7.583. So I'm just going to store this here, 7.583. And then what's my actual solution? It's 1.416 repeating, 0.083 repeating, 0.416 repeating, 0, 0. So I'm just getting these values from the actual values that the LP relaxation is. So what does this mean? This means that since I'm in a minimization problem, you need to make sure you factor in minimization or maximization, that the best possible solution I can get is 7.583. I can't get anything lower than that. What I also notice is that here all of my objective function coefficients are integer, and so when I force these variables to all be integer, so forget, like let's say I didn't have x4 and x5 not being integer. Let's say I forced them all to be integer. Then I know my objective function value has to be integer. So I can't ever get an objective function value of 5.5 because that would mean one of these variables carries on a non-integer solution. So here, what I gather from this is 7.58 is the least I can possibly get because it's a minimization problem, and this is the solution. I then have to check, do I need to branch? So here, are all my variables integer? No, they're not. Is this bound worse than the best known solution? Well, right now I don't have a best known. I don't have an integer solution, and I'm currently not infeasible. So that means I'm going to branch. And I'm going to branch then on any of the variables that aren't integer, that should be integer, that I need to be integer in the final solution. So here I'm just going to take the first one. I see that x1 currently is not integer, and I'm going to branch on it. And so now you need to decide what are the different constraints that you're going to add when you branch. So here, right now, x1 wants to be 1.416 repeating. And so we could say, okay, well, x1, you can't be 1.416 repeating because that's not integer. But we can do even better. So maybe you'd say, okay, you can't be 1.416 repeating, and you resolve it, and now it's going to be 1.42 something. But we know it can't be in between there. So we can say, well, you can be greater than or equal to 1, or greater than or equal to 2, I mean, or you can be less than or equal to 1. So I'm taking out this range between 1 and 2 that it wants to be and saying, no, you can't be in that range. So that's what I'm going to do here. I'm going to take this, I'm just going to, I don't know, place it somewhere here, and also going to branch down below. And so let me just insert some lines to make it more clear. And so up here, I'm going to say that x1 has to be greater than or equal to 2. And down here, I'm going to say x1 has to be less than or equal to 1. So I'm going to close that. And so now I need to continue. So if I take this top one, I'm going to keep my initial LP relaxation and just add the constraint that x1 has to be greater than or equal to 2. So to do that, I'm just going to go into solver, keep everything else the same, and just add the constraint that the decision variable x1 has to be greater or equal to 2. And then I'm still going to solve using simplex and see what I get. So here I see that, I'm just going to move this over a little bit. I get an objective function of value of 10.33 repeating, and my solution is 0.3300. So I'm going to do the same thing for here, and I'm going to solve for this node. I then need to go back into solver, keep my original LP, but now instead of saying x1 has to be greater than or equal to 2, I'm going to change this and say it has to be less than or equal to 1. And solve. And so solver found a solution. It has an objective function value of 11.5. So I'm going to put this down here, 11.5. And my solution is 0.502. And so now I need to decide, can I stop branching? Do I know an integer or a feasible integer solution, or do I need to keep on branching? So what this says up here is my new lower bound, because I'm in a minimization problem, is 10.33, and I still have some non-integer solution. So here x3 is 0.33. So I need to keep on branching in this node. Same thing here. I have a higher lower bound when I say x1 has to be less than or equal to 1, but still I don't have an integer solution. So I'm just going to do a greedy method. So I'm going to take the bound that is better. So we're in a minimization problem. This bound is better. So 10.33 is less than 11.5. And I'm just going to branch off of this top node. So I'm going to go here and I'm going to say, I'm going to branch on x3 because x3 is not an integer value and I want it to be. And so just add the lines real quick. For up here, I want x3 to be greater than or equal to 1. Because again, it wants to be 0.33. Or we're thinking that it wants to be somewhere between 0 and 1. And now we're going to force it to be on the outside of that range because we know in between 0 and 1 are all fractional and that's not a feasible solution. So here we're going to say x3 has to be greater or equal to 1, and now we want x3 to be less than or equal to 0. What this is really saying, so we already have a constraint here that x3 has to be greater than or equal to 0, and now we're saying x3 has to be less than or equal to 0. That's essentially saying x3 has to be 0. So we're going to do the same thing in our solver and solve for these two nodes and see what comes out. Well, when we do this, we need to make sure we still factor in that x1 is greater than or equal to 2. So here I have the constraint from the bottom node. I'm going to change this and say x1 has to be greater than or equal to 2. So that's the first thing I need to do, is make sure that this constraint here, because we're farther into the tree, that this is still apparent in my solver. Then I'm going to just do the top one and say x3 here has to be greater than or equal to 1. And it appears my first constraint here, x1 greater than or equal to 2, did not add. So let's just make sure I add that. So let's just make sure here I have x1, so what's in C8 is greater than or equal to 2. These are my bounds. This here, E8, has to be greater than or equal to 1, so that's the same thing as x3 greater than or equal to 1. And then this was my original constraint. I'm going to again solve with simplex and solve. So I found a solution, so I'm not infeasible. My solution value is 14, and the values for the decisions is 2, 3, 1, 0, 0. And so what do we know here? Can we stop branching from this node? And yes, we can, because we have an integer solution. So right now, this is our first feasible integer solution, and it has a value of 14. So all I'm going to do here is with this node change it to red so that I know I don't need to branch from it anymore. However, there are other nodes within my tree that I haven't stopped at, and I maybe can find a better integer solution. So I'm going to do this here, I'm going to change, and I'm going to evaluate this node. So again, I keep my same model. I need to make sure that x1 is greater than or equal to 2, but now I need to change this x3 to be less than or equal to 0. So I'm going to add that, and then I'm going to solve and it's found a solution, so it's feasible. If this, sometimes there's like a red exclamation point, or it'll say solver cannot find a solution. That means it's not feasible. It can't find a feasible solution. That's what you have to pay attention to this box. And so what do I see here? I see my objective function value is 12, and the solution is 2, 2, 0, 0, 0. And so I now have a better, it's integer, all the solution values are integer, and I get an objective function value of 12, which is better than 14. So this is now my best known integer solution because we're minimizing, so 12 is better than 14. I also know I can stop branching because I have a complete integer solution. So I'm going to change this to red. So up here, I'm done branching. I've reached 2 red nodes. I need to go down here and decide, do I still need to branch? And so here I realize that 11.5 is a better bound than 12, and therefore I need to keep on branching. What you could say is that 11.5, if we said that all of these values had to be integer, we know that an integer solution has an integer objective function value. You have to get one, and so therefore you'd have to get an objective function value of 12. But we do have these 2 values, x4 and x5, that can be fractional or continuous, and so therefore we need to keep on branching. And so here we're going to branch on the next fractional variable. So here I'm going to branch on x3 because x3 is 0.5 and it needs to be integer. So let's just add in these lines. And so here I'm saying, so it wants to be 0.5. So I'm going to say here x3 can now be greater than or equal to 1. You can't be 0.5. Or down here, x3 can be less than or equal to 0. And just like we saw here, we have an original constraint that x3 has to be greater than to 0, and now we're saying it has to be less than or equal to 0, so we're just forcing x3 to be 0. So now we're going to evaluate these 2 nodes. So again, the original model stays the same. I just need to make sure now that x1 has to be less than or equal to 1. So I'm going to change this. So C8 is where I store x1. I'm going to say it's less than or equal to 1. And now I'm going to change here x3. So I'm going to do the top first and say x3 is greater than or equal to 1. So let's just make sure everything went over. I'm going to solve with simplex and see what I can get. So it found a solution. Here, this solution has a value of 12, so I'm going to put 12 here. And its actual values, solution values, is 1, 0, 1, 0, 2. And so, again, I found an integer solution, so I know I can stop branching. I also know that this objective function value matches with my current best known solution, so this one. And so therefore, if 12 is my best solution, then I have multiple optimal solutions. But I don't know yet if I can do better than 12. So I need to explore this node and see if I can get something better than 12. And so here I'm going to solve for this node. And what do I need to do? I need to make sure x1 is less than or equal to 1, which it is, and now I need to make sure x3 is less than or equal to 0. So I'm going to change this to be less than or equal to 0, and I'm going to solve. Here, it's found a solution. The solution value is 17. I'm going to put this down here, 17. Or the objective function value is 17, and the solution is 10032. And so what do I know from this? Yes, I found an integer solution, so that tells me it's one of my 3 criteria, so I can stop branch and bound on this node. What I also know is that my new lower bound for this node is 17. And so I could compare 17 to my best integer solution. So what this says is 17. And anything, if I did branch elsewhere, that I can't get a better solution than 17. So you'll notice here, it's a minimization problem, so it's always increasing. So here, 7.583. Then I got 11.5. Then I got 12. Then I got 17. So I'm always going to be non-decreasing. So it could be exactly the same value, but it has to at least be greater than or equal to as I branch out. For a maximization problem, it's just the opposite. They're going to decrease or stay the same value. And so here, 17, I compare it to my best integer solution and say 17 is greater, so I can't get anything better than 17 later on, so I can stop branching here. So this satisfies essentially 2 criteria to stop branching. One, that it's an integer solution, and also that the bound is worse than my best node solution. So here I've turned all of my ending nodes red, and therefore I can say I'm done with my branch and bound tree, and that my optimal objective function value is 12, and I have 2 solutions that give me that value. This 22000, 10102. And so therefore I'm finished. So that is how you do a branch and bound tree. Remember, this is a minimization problem. It follows the same structure for a maximization problem. You just go through and are solving LP relaxations. So you should never have to go through and put certain values as integers in solver. I know you know how to do that, but that would be cheating according to solving this IP with branch and bound. You should only be solving where you have continuous variables. So again, feedback is appreciated. If you have other problems that you're working on, feel free to request a video, and also let us know how helpful this is with comments and a rating. Thanks!